All right, starting our new unit on calculus, specifically differential calculus, and it's just an introduction to this vast topic. Okay, don't be frightened by the name. Calculus is all about gradients, and gradients are rates of change. In other words, how quickly one variable increases with another. So differential calculus is this field concerned with rates of change. Okay, so we already understand gradients. Okay, and let's just kind of revisit that a bit by looking at the graph of these two straight lines. This red one would be y equals x plus 2, and the blue one here is y equals x. Different graphs, but they have the same gradient. Okay, their slope is exactly the same, they're parallel to each other, and because their slopes are the same, the rate at which y increases as x increases is both the same for both of these lines. So we can see if we start here at the origin for the blue line, we go across by 1, we go up by 1 to get to the next here. Go across 1, up 1, across 1, up 1. And that's the same here, even though there's a different starting point. We go across 1, up 1, across 1, up 1. We are moving along that same line. So they have the same gradient, the same rate of change. Now, when we are writing the gradient of a line, we use this variable m to represent gradient. So here we would say m is equal to 1. Okay. A gradient of 1 simply means that for every 1 unit that we move to the right, we're going up 1 unit to stay on the line. Okay, the amount you go across equals the amount you go up. That's for a gradient of 1. If, on the other hand, we had a line with a gradient of 2, then, well, for example, y equals 2x plus 1. Okay, here's our gradient, here's our m. Okay, that means that for every 1 unit we move to the right, we're going up 2 units. Okay, that's a gradient of 2. Across 1, up 2. If we had a gradient of 1 over 4, then that's the same if we think of a decimal value of 0.25. That means for every 1 unit to the right we move across, we're going up 0.25 units. On the other hand, we could think of it this way. If we move 4 units to the right, we're going to go up 1 unit. Okay, so that's a gradient of 1/4 or 1/4. Now, in calculus, rather than using m to represent the gradient, we use dy dx. Now, why dy dx? Well, because it comes from this notation delta y over delta x. And this delta symbol, when we think in terms of science usually, simply means the change. Okay, so delta y over delta x just means change in y over change in x, which is exactly what we're doing when we're calculating the gradient. Okay, so in calculus, dy dx is called the gradient. Is called the derivative. For linear functions, like we saw above, in the graph above, okay, where y is represented by the expression mx plus c, okay, dy dx equals m. Whatever this number is, that's what dy dx is. So in this case, for all linear functions, it's a constant value, okay, because it's always the same, no matter where you are on the line, okay, you have that same gradient, okay, the same rate of change. However, with non-linear functions, as an example, y equals x squared, the gradient is no longer constant. It's different at each point on the curve. Okay, so how do we deal with that? Well, let's start by just thinking of it in terms of an average rate of change. An average rate of change, a typical example every day that we use would be speed. Okay, a variable rate of change is speed. Now, when we travel from one place to another, we never move at a constant speed. Okay, we must start off slow until we get to our desired speed, which is going to fluctuate, okay, based on other people, vehicles, intersections that are on the road as well, that cause us to slow down, or we might speed up to overtake. Other factors, speed limits are in effect, okay, which vary as well. However, we can calculate the average speed over a particular distance simply by dividing the distance travelled by the time taken to travel it. Now, if we were to plot the graph of the distance travelled on the y-axis against the time taken on the x-axis, then the average speed would be the gradient or the slope of the line joining the start and finishing points. So, the way we work out the average speed, or the gradient, is simply the change in distance, which would correspond to the rise, over the change in time, which corresponds to the run. So if we have a look at this example here of this distance time graph, which you can see it's not a constant rate of change, it's changing. But if we pick 2 points on here, we can work out what the average rate of change is between those 2 points. So imagine a straight line passing through those 2 points. We can work out the gradient of that line. That'll give us the average rate of change between A and B. So our rise, which corresponds to the vertical distance between A and B, that would correspond here in terms of our y values, okay, and our run, which is going to be our horizontal distance between A and B, that's going to correspond to our x coordinates. So the average speed in this case would be our rise over run, which would be, what's our rise? Well, the difference in y values would be 30 to 12, okay, 30 minus 12, and our run is going to be the difference in the x values, so 12 minus 2, which is going to be 18 over 10, or 1.8, and our units are metres per second. So that is our average speed over between those 2 points. Okay, you pick a different couple of points, you'll get a different average rate of change. Okay, so in general, the average rate of change for a given function is using this rule. Okay, the average rate of change is f of b minus f of a over b minus a. Now this is exactly the same as our gradient formula, where f of b would be our y2, f of a would be our y1, b would be our x2, and a would be our x1, okay, and which is rise over run. Okay, so it's simply the gradient formula for joining 2 points. Alright, so let's think about that in terms of the function we have here. F of x is this quadratic, x squared minus 2x plus 5. We want to know what's the average rate of change for that function as x changes from 1 to 5. So for x equaling 1, f of 1 will equal 1 squared minus 2 times 1 plus 5, which is 1 minus 2 is negative 1 plus 5 is 4. And then we have x equals 5 is our other endpoint. So f of 5 will equal 5 squared minus 2 times 5 plus 5 equals 25 minus 10 is 15 plus 5 is 20. So our average rate of change, okay, from x equals 1 to 5 is going to be f of 5 minus f of 1 over 5 minus 1. F of 5 we see is 20 minus f of 1, which is 4 over 4, and so that's 16 over 4, which is 4. So that's our average rate of change. What does it mean? That on average, as we go from 1 to 5 in our x values, the y values increase on average by 4 for every one across. Okay, so as we go across from 1 to 2, then the value of the function, which started at 4, would go up to 8 on average. Okay, and same, just averaging up in that direction until we get to the value of 20 at the end. Okay, so that's what that is referring to. Okay, so that's how you calculate the average rate of change for a given function. And then you can go on with your exercise 17a for that.